going to show you now. Is it the recording has started? So hello again, back to Moodle. Come on, log in. Ain't doing anything. Oh, yeah, that's nice. This is your Moodle, the Moodle for nonlinear control systems. I'm afraid the title is written in Romanian. I really don't exactly understand how these things work because in some parts the title is in English. Here the title is in Romanian. Anyway, who cares? Your Moodle, you've got all the 5 chapters we're going to discuss in the beginning. Here we're going to add even more if we're going to add more topics to this class. You've got the books here. You've got the paper of the COVID spread, which we will probably study once again since when we are going to talk about n-dimensional systems. Then here you've got the papers to study and for exam. This is ongoing upload because we need to put more papers for you to be able to choose. You know the drill from DCR, so you're kind of familiar with these things. And then you've got here people who have studied nonlinear systems with me have already got these documents. These are exercises with and some sort of solutions manual for a couple of exercises from this class. Okay, this is the list, the exercise list inherited from nonlinear systems course. As you requested, here is my YouTube channel, the link to my YouTube channel. Just click on this, and I think it automatically takes you to the to my YouTube channel. And I added a short, fancy description here. Okay, right? And here's the first lab practice. It's a PDF with a couple of words in it. It's half a page. It's not much, but it's helpful. And this is the assignment. As you can look at it, you just need to click on the assignment, solve it, and then upload files to me, back to me, text and files, whatever suits you best, but files I need. So I need M files, MATLAB or Maple if you have Maple, but this is only about MATLAB this time. So you have 2 exercises, as you can see. First is an exercise taken from a book by Astrom called Feedback Control Systems, which is a very nice book. This is in that book, he talks about nonlinear stability, about Lyapunov stability, and which we are going to discuss as well. And he's got a couple of nice examples we are going to study at this class, examples I haven't used before. And this is a simple example, and he asks you if these equilibria are stable. Okay, you need to compute the equilibria of the system to tell us if they're stable or not. If there's more, if they're isolated, you have to tell all these things. It's not very difficult. Then you have to plot the f of x with respect to x and identify the equilibrium points on this plot. And then I'm asking you to solve this equation using ODE 45. Okay. Oh, I forgot to mention here, but I think it's easy for you to understand that you need to specify initial conditions. Okay. I'm going to adjust the text, but even if I do not, you realize that probably the plots or the solution of this equation heavily depends on the solutions heavily depend, because there's more, on the initial conditions. And you have to show me that. Okay, you have to show me that. Okay, because I'm asking you here, what type of trajectory plane are we talking about? Is it a plane? Is it a half plane? Is it only a band, like you saw with the Riccati equations? Okay, that the solutions are split in bands depending on the initial conditions, okay, that you set for this equation. Secondly, because I need you to practice on the ODE 45 numerical integration, I'm going to ask you to simulate this Lorentz attractor system. This is emphasizing from the first chapter the idea that a deterministic nonlinear system can behave chaotically. So you're going to see a chaotic plot. You can simulate this thing using ODE. It's not very difficult. The code to simulate a system of differential equations. That's very easy for you because you're all experts in programming. So this is not. I don't think it's difficult for you. You've got a week to do this. If you need an extension, you know I'm very flexible, so you can ask for an extension if you need it. Okay? You remember that from the model reduction course last semester. Okay, so I'm going to ask you to simulate, to numerically integrate this Lorentz attractor for different values of the parameters and of course of the initial conditions. And I need you to compare this to the Lorentz command in MATLAB. The Lorentz command in MATLAB is making a nice moving plot, behaving chaotically. Okay, so this is all I'm asking of you. I don't think it's very difficult, do you? I guess not. Okay. So you just need to solve these things and need to show me the results. Is this clear?
Yes.
Okay, fine. It's not difficult. Let's go back to the notebook.
One more thing. We still have the due date of the assignment as being today on Moodle.
Assignment can be. It should be 28th. Oh.
Today is 28th.
Oh, sorry, made a mistake. Yeah, I have to change this. Okay, I'll fix it because I need to fix the text as well. I'll adjust everything once the class is finished. Okay?
Okay, thank you.
Yeah, I'm going to make it for next week. I'm not sure what I was. Oh, yeah, that's because I started it last week and I didn't do anything until today. Okay, that's probably that's it probably. Yeah. Okay, I'll fix it. Okay, don't worry about that. Just remind me. You can use the chat of the class.
When will be the due date?
Next week. 2nd of November. What's next week? I have no idea. 5th of November, 6th of November.
4th.
4th of November, something like that. Something in the beginning of November. What? You were
I
saying
said
what?
6 is better.
6, 7, whatever. It's not so difficult. This, if you ask me, with your experience, and since you are kind of the good people here, I assume that 60 to 120 minutes is enough to solve this and answer to me. Between 60 minutes and 120 minutes. So 1 or 2 hours. I think that's not very much. Before you go to sleep, or if you wake up very early in the morning, or if you sit in the traffic and you have a nice device, you can solve it while you're driving, which I actually do not recommend. Right. Okay, so you'll get enough time, and if you need an extension, see, you remember what happened last time. That again, I was very flexible, so you can ask for an extension, and I'm going to grant you an extension. Okay, you don't need to worry about that. Okay, right? That's okay.
Yes.
Yeah.
Of course, it is okay. Again, I'm not exactly. I do not exactly. On my desktop, the OneNote has not recorded my notes. But if you look in your OneNote, probably you'll find what I wrote next to this to the slides. So these are a few examples of first-order systems we are simulating to judge about the stability, about the behavior of the system, and so on. Of course, you realize that from the very beginning that this is a very simple case of the scalar systems, and that the problem is that when we are going to go to order 2 and higher than 2, it's essentially not possible to analytically compute a time domain trajectory for the system. So we need to appeal to other methods. However, we are going to do that starting with the first order systems, where we can compare our qualitative results with the actual plots, And this brings me to the MATLAB I have prepared. MATLAB. So I need this, and then I need this. Okay. So this is the simple code that can be used for the it's a fly. That can be used for numerically integrating a differential equation. Linear or nonlinear, it doesn't matter. So the examples in this notebook here, which I don't know where. No, it's here. The examples here are these: ax, x minus x to the power 3. Okay. So it's ax. That's easy. Ax I'm not going to talk about. X minus x to the power 3 minus x squared and x squared minus x. This is the Riccati equation. Go back to the MATLAB now. And here it is. Yeah. So let's start with x to the power 3 minus x to the power 3 plus x. Okay. And let's run the simulation. The simulation is running. It's a very easy simulation, but this machine is a bit slow due to limited memory and limited CPU. But it's handy. Comes in handy. And we're going to see something nice. If you bear with me for a minute. Okay, these are the plots. Now you can see here you can see here when we are starting from a very nice initial condition. This is a negative initial condition. Yeah, the system, the trajectory goes to -1. If it stops and it's content at -1, that means that -1 is the equilibrium point, which is an equilibrium point. If you just compute minus x to the power 3 plus x equal to 0, the solution, the unique solution is x, the unique real solution is x equal to 1. So we can see here the -1 equilibrium. You can see here the -1 equilibrium. Okay. If we start from minus 0.5. On the other hand, if you start from the positive initial condition, right? You can see here, you start from the positive initial condition. Yeah. You can see here, it's going again to the equilibrium. So this equilibrium in 1 is also stable. Where can we see these equilibrium points? Because what is this plot? The second plot is f of x, which is minus x to the power 3 plus x versus x. Okay, it's a sort of a phase plot, easing the analysis for us, and we can see here that it's 0. Yeah. Okay, this is not very accurate, but it's essentially this is the idea of this plot. It's 0 in -1 and 1. Okay, it's 0 in -1 and 1. So these are essentially the two equilibrium points. So what kind of, and if you go with a higher initial condition, say take a large initial condition, say 5, you see, it's going back to the equilibrium in 1, okay? So 1 and -1 are the two equilibrium points, or the two equilibria of this equation, okay? And the trajectories are what? Are living in a band between 1 and -1, or if the initial condition is larger than 1, they are living in a half plane, okay? In a half plane, okay? Okay, and the two equilibria can be seen on this plot, okay? Then we were having minus what? We were having x squared minus x. So this is a plus, and this is a minus, and this is the Riccati, which we remember from last week. Okay, x squared minus x minus x. We run it. Okay, now this, if you start with the initial condition 5, nothing, this is wrong. Yeah, as we can see here, the only equilibrium point is probably in 1. Yeah, it's the only equilibrium point if you check the second plot. Yeah? If you check the second plot, the equilibrium is in 1. Okay. This is not good. Let's start with the lower initial condition. Okay, so if you start quite close to the initial condition, well, actually the equilibrium should be 0 here, not 1. Should be 0. In 0, the plot, the second plot is not very accurate. It should be in 0. In Maple, these plots are much more accurate than in Maple. In Maple, sorry, they are much more accurate than in MATLAB. But as you can see here, if you take an initial condition rather close to the equilibrium is also appears to be stable. Let's go a little bit further. You see, if you go, if your equilibrium point is much higher, okay, if you're very far away from the equilibrium point, you see, if you're here or here, yeah, you cannot go back to 0. You cannot go back to 0. Only if you're very, very close. If you're very, very close. Okay. So this looks like actually it's not very stable in this way. It's not very stable in this way. The funny thing is what happens if you change the signs. If you change the signs, minus plus. What happens if you change the sign? Minus and plus. Well, things get a little bit better. Okay, the graph of f of x with respect to x is this one. Okay, is this one. So it goes back to 1, which is a stable equilibrium point. Now, if you go really far away, again, what happens? Nothing happens. So apparently 0 in this case is a stable equilibrium point. 0 wasn't stable in the previous case, x squared minus x, but 0 is a stable equilibrium point in minus x squared plus x. Okay, let's see what happens if you go negative. If you take a negative initial condition, you remember this discussion from last week, then you've got a problem, because here you run, if you see this kind of graph here in -4, yeah, at time -4, you probably run into what? What is this? It probably goes to minus infinity. What kind of a point is this? What kind of phenomenon is this in 4.1, minus 4.1? And this is probably a vertical asymptote. This is probably a finite escape time, when the trajectory goes boom at some time instance. You see? This is a vertical asymptote. So these things are quite interesting, and the analysis is different from what you do in the linear case. It's different from what you do in the linear case. I'm going to stop sharing the screen here. Okay. All right. And I'm going to go back to the slides. Okay. Here's the slides. I'm going to share the screen now with you. Share screen. Oh, Diana is here. Hi, Diana. And Melania is here. Hi, Melania. Everyone's here. Cool.
Hi.
Hi there. Where were we? Right. The school book. Okay, so this is where we stopped last time. The examples we have seen in MATLAB. So we are going to talk about stability. How do you assess? Because of course you cannot assess the stability of such a nonlinear system computing trajectories, because we cannot compute trajectories. We cannot do that. How do you compute trajectories? You cannot do that. That's complicated. So we have to define the stability concept. Okay, this is the sensitivity. It says here it's actually the sensitivity of the solution with respect to initial condition. And we have seen that. Some negative initial condition in the Riccati equation was leading to a finite escape time. That's not stability. Okay. So this is what stability is now. It's the stability of a trajectory. It's the stability of a point X. Is no longer the stability of the whole system, or input-output stability, as you know from the second year. This is no longer true. This is a different kind of stability. Of course, the idea is the same, that it does not blow up. Okay? So the definition of the stability is that if you have an equilibrium point, the equilibrium point is stable if small variations from the initial condition, if the small variations away from the initial condition, okay? So if the initial between the initial condition and the equilibrium point, the variation is quite small, then this leads to a small variation in the trajectory as well. The trajectory does not blow up. This is what happens here. So this is kind of local, if you look very closely. This is local stability. This is not a global property. This is a local property. It's asymptotically stable, of course, if this condition occurs. If the trajectory asymptotically follows the equilibrium point, yeah, trajectory asymptotically follows the equilibrium point. That's what stability is, and you have seen in the plots. Yeah, you saw that in the plots. Okay. And another notion of stability, exponential stability, if you have this kind of exponential boundness, okay, this kind of condition. Of course, in the linear case, it's very easy to prove, and you can do this yourselves, that in the case when you have x dot is minus ax with a larger than this 0, it's very easy to see that all that 2 and 3. So in the linear case, 2 and 3 are actually equivalent. 2 and 3 are actually equivalent in the linear case. And that's not very difficult to prove. Since stability is seen as a local property, so that means if you veer off very slightly with your initial condition from the equilibrium point, and the trajectory goes to the equilibrium point, that's stability. Okay? That means small variations are always related to linearization. Small variations, you remember from the pendulum. Yeah, you remember from the pendulum that if the angle theta is very, very small, then sine theta is approximately theta itself. And we have seen that. So this is what first approximation means, when you can write this kind of approximations, and you can assess stability just by looking at these approximations. So local stability can be easily inferred from the analysis of the linearized terms around the equilibrium point. Okay, you have seen these things also in simulation course in the 3rd year. You have seen this in control engineering course. You have seen this before probably, but this is where we properly formalize it and we definitely settle things. Okay, how does this work? Yeah, we linearize the system through the first order for the first order approximation. You take psi to be the difference, the error between your current trajectory and your equilibrium point. Okay. Then psi verifies the differential equation psi dot is f of psi plus x star, because this is x and this is x dot. True, right? Because if you do psi dot is x dot minus x star dot, but this is 0. You agree? So psi dot equals to x dot, right? Equals to x dot. And in this case, you can easily write this thing. And if you can see, as you can see here, this is the term that counts. Of course, we could write here plus, we could write here plus f of x star. But since x star is an equilibrium point, this is 0. That's why we don't write it anymore. This is the Taylor series approximation of f. Okay. We can write the Taylor series, or f admits a Taylor series expansion because it's analytical. It's usually a smooth function. Okay. Of course, we drop the higher order terms because we're talking about very, very small variation. This is very small, very small. And since this is very small, the higher order terms are are going to 0. So they can be neglected. They don't go away totally. They're only neglected. That means that around the equilibrium point, you can study this object, number 14. You can study this object. Okay. It's a different object. It's very different from the original system, but it explains the behavior of the original system near the equilibrium point. Okay. The general solution of such a system is this one. We know this from first order systems, is e to the power f prime of x star times the initial condition of zeta. This is zeta. Okay. Since if this derivative is negative, if f prime of x star is negative, then this term goes to 0. This term goes to 0. Okay. I think there is a slight mistake here. What's the mistake here? See it? There is a t missing. There is a t missing. So now if f prime of x is negative, this goes to 0 when t goes to infinity. Okay, this goes to 0 when t goes to infinity. Okay, right. Okay. Of course, then you can also show that this property happens, if this is very, very small. This is very, very small. And now we have the result. We have the result of the stability by the first approximation. Once you've got a nonlinear system 8 with f smooth, of course, continuously differentiable, an equilibrium point that satisfies this condition, f prime of x star is negative, is exponentially stable. Okay? Is exponentially stable, which is quite strong. Note that we have to make the following remark. Theorem 6 is only sufficient and not necessary. And not necessary. I'm afraid this is only a sufficient condition, and you have to get used to that with nonlinear systems. With nonlinear systems, we work with sufficient condition, not necessary and sufficient, unfortunately. So this is only a sufficient condition. It's sufficient to have the... So that means there exist stable equilibrium points. There might exist stable equilibrium points that do not observe this condition of f prime of x negative necessarily. Okay. However, if we already know that this condition happens, then we are sure that the point, the x star is stable. The x star is stable. Okay. So now, if you look at our examples, we can easily draw the conclusion. Yes. So if you have x dot is minus x to the power 3 plus x, that means f prime of x equal, no, first of all, the equilibrium points. So this means that f of x is minus x to the power 3 plus x. The equilibrium points minus x to the power 3 plus x equal to 0. That means x squared is 1. That means we've got two equilibrium points. Yeah, x1 star is minus 1, x2 star is 1, just as we have seen before. We saw in the MATLAB simulations. Okay. Let's see about their stability. F prime, the derivative, yeah, f prime of x. So this is df of x with respect to dx. Okay. This is what? Minus 3 x squared plus 1. Okay. Now, that means that f prime of x1 star equals what? Minus 2. This is negative. So that means x1 star is stable in the exponential sense. And f prime of x2 is what? Is also minus 2. So that means x2 star is also stable. Okay. This is also stable. Okay. Have we been talking before about oh yeah, we have talked about these things, about this plot. We have seen this plot. So you can easily recognize these things from this plot, okay, which is f of x with respect to x, okay. Now, f prime of x is usually the tangent to this thing, okay. So you can compare this. We've got two ways to assess stability, okay. We've got two ways to assess stability, okay. One is use f of x plot and see who's an attractor and who's a repulsor. Two, use the first approximation. Okay. If you have questions, please. If you have questions, please. questions, please.
Tudor, good evening to everyone. You can hear me?
I can.
Yeah, okay.
We are recording, so you can shut off your camera if you're.
Well, I have no issue with that, but I think there is some echo, at least for myself, when talking.
Fine.
No, but that's okay for now. Camera is fine. So no, I have no questions. So I would have encouraged maybe the students to put some questions, or just let them another example work out. That would be maybe better.
Yeah, I do have. I wanted to show. I didn't know you were joining now because I wanted to show them. I have a population growth model of also
Yeah,
first order equation. That's fish in a
right.
pond, and that's a very funny example. I always show it in the nonlinear systems class, and I want to show it here as well, which is very nice to see the equilibrium of the fish growing, the fish dying, and funny things like that.
Yeah, fine. I have just prepared a small example on how to make some simulations of nonlinear system in MATLAB. I think I will need like, I don't know, maybe at most half an hour. So you have now to schedule a little bit. Will you make a break for 10 minutes and then I will start? Or
Actually, I can have a break now and you can start in 10 minutes. I don't mind. I can explain my stuff later.
Or you run the example first. Yeah.
I don't have the running now. I showed them in the beginning some MATLAB. My example is on pen and paper. It's just doing the computations for the.
No, but after I'm coming, let's say in 10 minutes with the MATLAB issues,
Okay.
maybe then take as exercise to write a small. Yeah, but not for now. You know, for next time.
They have an assignment. They already have an assignment for next week with 2 examples to write the MATLAB code for numerical integration and to integrate them and then explain.
Okay.
There is an assignment already for them ready for them on Moodle to do until next week. I just have to crush it a little bit and then it's ready for them to solve.
Yeah. Okay. Good. So
let's have a break, then.
I will be then back at 7 p.m. point. Okay.
I'll just stop the recording for now because there is